Okay, a good way to review Chapter 3 is to go back and look at a bunch of old test problems. Here's one. This is a fixed point iteration from section 3.4 where g is x plus sine of x. It has roots at any multiple of pi because you plug in any multiple of pi here and you get 0 plus n pi, and that's equal to n pi. So if you start at n pi, you don't change. The question is, well, two of the roots are 0 and pi, n equals 0 and n equals 1, and analyze each of them to see if they converge and the order is. Well, the key thing in section 4 is that the fixed point iteration xn plus 1 equals g of xn will converge near the root r if and only if g prime of r is less than 1 in absolute value. So we just, g is x plus sine of x, g prime is 1 plus cosine of x. At the root r equals 0, that's 2, so it diverges. At the root pi, that's 0, 1 minus 1, so that converges, and not only converges, it converges quadratically. So you take the second derivative to make sure it doesn't actually converge cubically, and it doesn't matter what the second derivatives are here because this is already not going to converge. So we're just looking at this one. So this next derivative is minus sine of x, and at x equals pi, sure enough, that's 0 also. So it's at least third order. And you take another derivative, and you plug in pi there, and you don't get 0. So, and by the way, it doesn't matter whether the second or third derivative are greater than 1. If the first derivative is 0, it's going to converge regardless of what second or third derivatives are. But the fact that the second derivative is 0 means it converges cubically, which is unusual. So it's, at pi, it converges of order 3. At 0, it doesn't converge at all. Here's a Newton's method problem. We saw how to find the square root of b by solving x squared minus b equals 0. If you want the mth root, then you just solve x to the m minus b, because the root of that is b to the 1 over m power. So this is just a generalization of what we did. So there, f of x is x to the m minus b. F prime is m x to the m minus 1. Just simplify a little, and there you are. And this problem, well, we saw how to solve 1 over x minus b equals 0 using Newton's method, and that gives you the root 1 over b, and we were able to simplify Newton's method to where it didn't involve any divisions. Therefore, that was a way to find 1 over b without doing any divisions. This problem says, well, can you do that with secant method? And well, there's f of x, and here's f of xn minus f of xn minus 1 over xn minus xn minus 1. There's 1, 2, 3, 4, 5 divisions there, so it doesn't look very promising. But you can simplify, the b's cancel and get a common denominator and so forth. After a bunch of simplification, sure enough, you can get rid of all the... So you can actually find 1 over b without doing divisions using secant method as well as Newton's method. There's not much point of using secant method because it's a little slower, and it's not hard to find the derivatives, so there's no advantage of secant method, but it's a good test problem. And it says if alpha of x is x minus 3 to the 7th power, so 3 is a root of multiplicity 7, will Newton's method converge when you're close to 3? And well, we did some analysis that showed that if alpha is x minus 3 to the 7th power times some q of x, then it's going to converge, but only linearly. This time the q is just 1, so it's simpler analysis. So f is x minus 3 to the 7th, f prime is 7, x minus 3 to the 6th. You just simplify, and take the, so this would be 6/7 xn plus 3/7, and the derivative of that is 6/7, so g prime is 6/7, so it does converge. In fact, if you subtract r from both sides, 3 from both sides, you'll see en plus 1 is equal to en minus 1/7 en. So en is exactly 6/7 times en minus 1. So after n iterations, you've multiplied the original e by 6/7 to the n. So it definitely converges, but only linearly, as you'd expect. from the analysis in section 3.5. Okay, here's a fixed point iteration. The g is x plus c f of x, and if r is a root of f of r equals 0, then you plug in r on the right hand side, that's 0 and that's r, so you just get r. So if you start with r, you'll stay r. So r is a root if r is the root of f of x equals 0. It says, how should c be chosen in order to ensure the fastest convergence? Well, g of x is x plus c times f of x, so g prime is 1 plus c times f prime of x. You plug in x equal to r, you get 1 plus c times f prime of r. And if you want it to converge fastest, you want that not only be less than 1 in absolute value, you want it to be 0, so it'll converge quadratically. Solve that for c and you get minus 1 at f prime of r. So basically the method would be xn minus f of xn over f prime at r, which looks a lot like Newton's method, except the denominator is f prime at r instead of f prime of xn, and it does converge quadratically. So you might say, what advantage is there of Newton's method over this method? Well, the advantage is you can't use this method because it assumes you already know r, so every iteration you have to already know r, because it's so it's kind of a useless method. But if you did know r, then that would be the best choice of c, and it would be as fast as Newton's method, but of course you don't know r. Here's a bisection method problem. If you start with a equals minus 10, b equals 10, and how many iterations do you need to get error of 10 to the minus 10th? Well, your original interval is b minus a, which is 20. After n iterations, you've cut that by a factor of 2 n times, and you want that to be down to 10 to the minus 10, so you just solve this for n. 20 over 10 to the minus 10 is 2 to the n. Take logarithms, it's about 38. And here's a experimental order convergence problem. This is kind of a common problem in my tests. It says if 3 consecutive iterations give errors of 10 to the minus 4, 10 to the minus 7, 10 to the minus 14th, what is the experimental order? And it doesn't tell you what method it is. You don't need to know the theoretical order. Just, you try some method and here's the results. What's the experimental order? Well, this error is assumed to be m times this error to the alpha. This error is assumed to be m times this error to the alpha. And you're interested in alpha. You could solve for m also, but you don't care much about m. You're interested in alpha because they ask for alpha. And so you just divide the two equations to get rid of the m, and then take logarithms. Well, you don't even need to take logarithms in this case because e to the 3 alpha is equal 10 to the 3 alpha is equal to 10 to the 7th, therefore 3 alpha equals 7, therefore alpha is 7/3. Here's another experimental order problem, except that instead of giving you the errors, they give you the x's, but they tell you the root is 5, so all you have to do is subtract 5 from each of those to get the error. So basically it's telling you that the 3 consecutive errors are 0.01, 0.0001, and so forth. And so it's just like the last problem then, except a lot of students just assumed this was the error and it didn't subtract the 5, and of course they got a order of about 1. If you do it correctly, the order turns out to be about 1.61, and it says what method have we studied that has approximately that order. Of course, that's secant method. Here's Newton's method and secant method to find the root of b minus 1 over x equals 0 without any divisions. We've done both of those already, so we'll skip that. Here's a fixed point iteration trying to find a root of this cubic polynomial. One way to do that would be to take everything on one side except the x cubed and then divide through by x cubed, and you get this. So if this converges, it'll converge to a root of the cubic. So basically this is your f, and the right hand side here is your g. And the question is, will it converge near the root of 1.839? That's one of the roots of this. Well, there's your g. Take the derivative of g, plug in 1.839. It turns out to be between minus 1 and 1, so yes, it does converge. Another experimental order of convergence problem, exactly like a couple we've already done, so I'm just pointing out that this shows up often in my tests. You need 3 consecutive errors because you need 3 errors to get 2 equations for m and alpha. And you divide the 2 equations, get rid of m, and then solve for alpha. Here's a fixed point iteration problem. It's similar to some of in your book where there's a parameter a. The right hand side is x plus a sine of x. And you're supposed to analyze this, but for a general a. So g is x plus a sine of x, so g prime is 1 plus a cosine of x. And at the root pi, we'll see if no matter what a is, if x is pi, that's 0. So you start at pi, you stay at pi. So that is a root. And the derivative at pi then would be 1 plus a times cosine of pi, which is minus 1, so 1 minus a. Now is that less than 1 in absolute value? Well, it depends on what a is. And if a is between 0 and 2, it will converge. It will converge near the root pi. If a is not in that range, it won't. And if a is 1, g prime at the root will be 0, and you get quadratic convergence.